It's a pleasure to be here. Thank you, DK, for inviting us to this meeting. It's been wonderful to hear all the presentations. And when I put these presentations together, I was thinking of so many different topics, especially in terms of the applications that we run on our systems at Sandia and our sister labs, Lawrence Livermore, which you heard from Adam Moody, and also at Los Alamos. Not many of you probably know about Sandia Labs. Sandia Labs, Los Alamos, and Lawrence Livermore are the three Department of Energy NNSA labs. And so we collaborate with a lot of our acquisitions plus on technology. So there's a lot of interaction between the three labs. So today the focus of my talk is really on our experiences with applications at Sandia, and in particular, some of the challenges that we face with our applications with MPI performance. So once again, Sandia was started in 1949 by President Truman, and it was actually run by AT&T Bell Labs in its initial few years. So it has a long history of contributing to the national security needs. And I won't go into all the details, but for those of you who are not familiar with it, I just thought I'll mention that. We also have different facilities. The main facility is located at Albuquerque, New Mexico. I don't know, some of you probably don't even know where Albuquerque is, but if you watch the old Disney cartoons, you probably would make left at Albuquerque. So that's Albuquerque, New Mexico, in the middle of nowhere, but it's a beautiful place, and if you get a chance, you should visit New Mexico. We have also a facility at Livermore, very close to the Lawrence Livermore Laboratory, and at Tonopah, and also at MVAPICH. As you can imagine, a 10,000 strong research institution with focus on national security would have a lot of different areas that take up our expertise. It includes materials, engineering sciences, nanotechnology, biosciences. Of course, computer science now is recognized, especially high-performance computing, as the third leg of research. And so there's a lot of investment made, and along with Lawrence Livermore and with Los Alamos, we have some of the very big systems. Previously, when NNSA was sort of equally distributing the funds among Lawrence Livermore, Sandia, and Los Alamos, we all used to get our own separate capability class sheets. And but a few years back, they decided that they don't want to spend money that way. They sort of tried to leverage, and so we formed a partnership between Sandia and Los Alamos. It's called the ACES partnership. And so the acquisition of very large systems is jointly done by Sandia. And you probably read in the press about 2 or 3 weeks ago of the acquisition of our next generation system called Trinity, which is a Intel mic based system. So to give you some, before I get into the MPI, I thought I'd give you a quick glance of some of the systems we have. This is very similar to the slide that Adam put up for Lawrence Livermore, but I don't have the big capability system. It's just the capacity computing system. I don't know if you want to go through all of them, but I'm going to be referring to 3 systems in this chart here. The first one on top of the one is called Red Sky. It's a few years old. It's a Nehalem Mellanox Connectex QDR, large capacity cluster. And then more recently, all the 3 labs got what do we call it, the TLCC, Tri-Lab Capacity Computing Cluster 2. That was our second sort of round of procurement of these capacity clusters. The vendor for that is Adagio, and that has 1232 nodes. Here, I want you to remember the name Chama, and the 1232 nodes, about 19,000 cores. At that time, the QLogic performance was slightly better than Miniapps, and so when we did the procurement, we had the QLogic on that system. But you can see that we do have both the InfiniBands of Miniapps and also the QLogic interconnect. And more recently, on the red side, you see this second one called MS, and that's the most recent acquisition. It's a much smaller system than Chama or Red-Sky, but it's got the newer Miniapps Connect X3 FDR interconnect. So if you remember the names, Red-Sky, Chama, and MS, that's sort of related to the two of them have the Sandy Bridge, 2 socket nodes, and then the Red-Sky had the old and the Hell processor. So you'll be able to appreciate when I show some comparative performance between them. The other big system that we have that again I'll be showing some of the performance is Cielo. Cielo is about 4 years old now, but it's a big petascale system. It's a Cray XE6, and it's got over 143,000 cores. So it's a very large system. It has a many-course, AV many-course processor, a dual socket, and the interconnect is the older generation Cray interconnect called the Gemini interconnect. We also have some advanced architecture systems, and I won't go through all of them, but these are meant to really help us move our codes to what you know, a lot of the focus of talks here in terms of you know, the Intel mic or the NVIDIA products. So again, in view of the time, I'll sort of rush through some of these slides. But I do want to point out that we have 2 things that you should be aware of. One of these advanced architecture systems that we have, including now some ARM-based systems that we are hosting, should be of interest to you. They're all in the open, and that together with what we call as the Miniapps, which again Sandia has led in the development of Miniapps, Miniapps. In fact, I'll show you the whole list of that here. There's a whole bunch of lists, and they're all supposed to sort of capture the essence of something, like Minighost captures stencil computations, and the communications associated with that. Mini-AMR, you know, for adaptive mesh refinement and so on. Mini-MD, molecular dynamics. So with this, you're sort of able to drill down into compiler questions or interconnect questions and so on, without having to spend a huge amount of time understanding very complex codes, which are typical of most Sandia codes. Okay, with that, what I'm going to do is talk a little bit about some of the challenges that we face with our applications. And I'll be focusing a lot on Chama, the capacity cluster. So when we got Chama in 2012, 2013, you know, it comes with MVAPICH installed in it because we work a lot jointly with Livermore. And so first thing we do is we run all the you know, acceptance tests on it, do all performance studies on it. And this slide is sort of summary of some of that. There's a complete description of all our acceptance tests and how well this particular cluster with the Sandy Bridge and QLogic InfiniBand did so well. This is, you should put it in the context of, you know, in my 10 years at Sandia, 12 years, we've been comparing MPP machines, which are typically Cray systems with custom interconnect, against commodity interconnects like InfiniBand or before that MirrorNet. And we have never seen in the past a commodity interconnect perform as well as the MPP machines, especially when you go to larger scales. Like typically a 256 core, a 500 core, the performance used to drop off. So here's a couple of examples of how this new commodity interconnect is really coming along and helping us scale to larger And so this is a very important example for us because many of our codes, as you can imagine, because they're all engineering, science, solvers play a very important role. Implicit codes, I mean. And so Sierra IS, one such implicit CFP code. And the top chart shows the strong scaling, and it's got the plot of REST-I, CLO, and Chama. As you can see, REST-I, a previous generation commodity cluster, after about 2 to 6 processes, the scaling went to parts. But for the first time, with Chama running MVAPICH, we really were able to perform very well, and we were able to perform as well as an MPP machine like Gray. So that was really very comforting to us. And then so we dug into it and said, what is the reason why we're able to do so well? And it turns out that for many of our applications, especially with an ML preconditioners, your solver ML preconditioners, we have very small messages in the 1K to 4K message sizes. And so the message rate is very, very important. So this shows the message rate, the ratio between Chama and CLO. Although with the proprietary interconnect in the previous generations, the proprietary interconnect like Gemini or Redstone interconnect were all there, but this time you can see that was the QDR InfiniBand gave us a good performance in the message size of interest in the 1K to 4K range, and that explains the performance. So I ran a comparison of MVAPICH and OpenMPI. I should say that at Sandia, a lot of codes still use OpenMPI, and but I was happy to see that MVAPICH, again, the message size of interest to us in the 1K to 4K range shows that I could perhaps see a 1.5 to 2x performance over MPI. So I need to work with my code developers to try and get them to use it. And so I tried one example of another code, Sierra Nalu, so again it's a CFP implicit code. And you didn't see too much of an improvement, but the MVAPICH showed about 2 to 3% better performance than OpenMPI. But interestingly enough, one thing that always bugs us, and I'm sure it all bugs all of you, is that when you see runtime variability between run to run, especially our codes go through a lot of regression testing, and so you don't want to see, from one day to another, not attributable to the code modifications I made, but for some other unknown reasons, the code runtime varies. So we like to see lower runtime, and we did see lower runtime with MVAPICH. I don't know what the cost for that is, but I thought I should share that with you. Another one is Sierra Adagio. This is a contact algorithm. From an MPI point of view, is the most demanding. So again, we're able to drill down into what the reason for it is. The growth in the all-reduced time. And when I say growth in the all-reduced time, it's not in the binary tree implementation of all-reduced, but a profile like MPIP tells you it's all-reduced time. What's happening under the hood is that, if you break down all-reduced into the actual time for the all-reduced plus the sync time, as it's called, and all the processes get the all-reduced. So what this tells me is that MPI 3.2 with asynchronous communications that helps us look at overlapping computations of communication should be a big help for codes like Adagio, which are really quite demanding in terms of the message exchanges. Another example is all-to-all-B. Of course, you can imagine all-to-all-B is used in so many any kind of spectral codes, so many other instances where it's used. Perhaps you could get away with using all-to-all if you can pad it so they're all equal length, so you don't have to stress the all. But many implementations of all-to-all-B is not very good. And here I pick up Cray because, here's a comparison with Sequoia, which is an IBM machine, and Zero, which is a Cray machine. And you can see the drastic performance difference impacted by all-to-all-B. And so this is just to tell you that globals are very, very important for us. So I took the 3D FFT code, and in this case I compared MVAPICH with OpenMPI. And for this particular message size that was of interest to us, with the 1K by 1K by 1K 3D FFT. The message was in the 16K to 32K range. And so I was able to get about 20% better performance with OpenMPI than MVAPICH. So maybe you folks can make the, I think I learned from this presentation that if I were to set the rendezvous to eager protocol, you might have probably be able to do that yesterday. So CTH is a very important hydrodynamics code for us. It runs for very long times on many of our systems. So one of my colleagues said, okay, make a comparison between MVAPICH and OpenMPI with CTH. And it gave anywhere from 2 to 11% better performance than OpenMPI. I don't have time to go through all the details, but I think it's dominated by nearest neighbor communications, and all-reduce is a very important factor. So I did look at all-reduce performance on a slightly different machine. This is on MS, which is got the newer Mellanox connector in it. But as you can see, in the first chart on the top was in the MPI task on the x-axis, the time ratio between OpenMPI and MVAPICH. And so it seems like there's some benefit for us looking at using MVAPICH for some of our cores that heavily use all-reduce. The bottom chart, I really don't understand why it's sort of strange looking performance, but this is on a system that nobody else was there. I got the whole system because it's a new system that we need to use to the usage. And so I ran message size up to 1K, 1 megabyte, and so the time rate was maybe something wrong, but I was surprised to see orders of magnitude differences in the performance between OpenMPI and MVAPICH. So I guess the bottom line of my presentation is that MPI is critical for many of our applications. What I heard here in the last day or two with the things that you're talking about, with MPI 3, asynchronous rules, topology of air communications, all of that I think can have a huge impact in reducing our time to solution of our problems for our applications that runs several days at length. And these things can really translate into big dollars in terms of the amount of time that's saved by efficient use of the machine. So that's basically the message that I have. Of course, I didn't mention also that sometimes we run into bugs with different MPI, and it's really tracking it down when it happens after some few hours of simulation is a non-trivial task, although we have tools for it. So robust MPI is very important to us. Of course, performance already talked about. I shared with you a few cases that I told you the importance of the MPI message rate being very, very critical for all our solver-based applications. I shared with you some OpenMPI and MVAPICH comparisons. This is not to get into a pissing contest, like we say, but I think it's still because anything that we can pass on to our code developers, users, in terms of the time that they can save in production applications is important. So that's the motivation for that. I think I have the bullet there in terms of how to extract the best performance. Every vendor that I've listened to presentations on MPI gives me 100 environment listings. So it makes it a really difficult task. And you really have so many systems, so many applications, different releases of MPI, different tools, all of that put together. So I'm just sharing some of the difficulties, but I think meeting a conference like this is really helpful to hear what all your experiences are and take that back to our users here. That's all I have to say. Thanks for your attention.
Thank you, Dr. Rajan. Any questions?
I just want to add a comment. What is happening, this is for your information as well as for others. If you take a proprietary system, which IBM losing, one kind of systems. They can tune and everything works fine.
Yes.
But when you are thinking of like even let's say MVAPICH or OpenMPI, these are for commodity clusters.
Yes.
And commodity clusters now there are so many varieties.
Yes.
Like all different kinds of processors, all different kinds of network.
I agree.
It's practically impossible to come up with the best set of unique parameters for that cluster.
That's why you give us the option to play with the environment variables so that we can try.
Recently, the some of our releases, what we have done is we are trying to provide some more intelligence, like in the build time,
Yes.
it actually detects what kind of processor speed,
Right.
the network,
Right.
it detects, and then you can do some tuning.
Yes. Yeah, but certain things like all-to-all, I think it's used so much, right? Any spectrum code uses. So I think the fact that the IBM engineers spent a lot of time on Sequoia, and of course Sequoia is an inherently powerful network because of the communication to computation balance. So so it does help there. But we did point out to Craig that they need to improve their all-to-all because otherwise when our users use all the system. They use Sequoia, they use CLO, they use our commodity clusters, TL60, depending on the kind of simulations they do.
Yeah, so we can work with you and then see like based on your communication pattern what should be the guidelines to
Yes.
use and do some offlines.
So in your already used example,
Yes.
is that already actually overlappable, or is it just collecting a residual peak bytes?
Are you talking about in the application?
Yeah, yeah. So
It is overlappable because